What I do want to go over with you, and this is new, is our decay formula. And with this decay formula, what I will say with this is it looks complicated, but let me take you through what it is, and then I'll show you how to solve this, how to plug in each part of the equation, and then you'll work through a bunch of these on your homework and you'll get this. I remember when I was a student looking at this going, what am I doing? But this will get easier as time goes on. And a lot of it, you're just gonna have to trust me that, hey, here's how you do it this way and you'll get it right, okay? So let me kind of tell you what the decay formula is. When we're talking about radioactive isotopes that we work with, they're constantly decaying, right? Which means they're constantly getting smaller. They're giving off gamma rays or whatever kind of rays with whatever isotope we're using. They're giving off energy and they're constantly getting smaller. And this helps us to be able to calculate that. What you might see on your homework is something that will say, I have 10 millicuries of technetium-99. What will the activity be in 2 hours? Okay, and this will help you figure those kinds of things out. So let me kind of identify what each of these are, and then we'll go through some. So this is activity, the activity you have right now. So current activity is equal to the original activity. That's why there's this O subscript. So current activity is equal to original activity times the logarithm of negative lambda times time. Now, if you feel like I just spoke another language, don't worry, I'll fill all that in and help you understand. When we talk about a logarithm, we're talking about something that either grows or gets smaller in an exponential way. What do I mean by that? Well, let's take the thing that we all are thinking about that we can't get away from right now, and that's COVID, right? So if I have COVID and we say that I can get 4 other people sick, and then those 4 people get 4 people, and those people get more people, that's exponential, right? You have exponential growth. Every time it grows, it gets larger and larger. So that's something growing up. When we work with radioactive decay, we start with a certain amount and it exponentially gets smaller, okay? So that's why we have a logarithm in there, because that's showing us how that radioactive decay works. Now, negative lambda times time. Lambda is what we call decay constant. It represents that constant decay, okay? Lambda, and this is one of the things that you just need to trust me on. I won't get deep down into the science of why the numbers are what they are, but generally will help you understand. But lambda is equal to 0.693 divided by the half-life of whatever isotope you're using. So again, this will be, if you're using technetium, it's going to be 6 hours, right? If you're using I-131, it's going to be 8 days. If you're using rubidium, it's going to be 75 seconds. Okay, so that's where this comes from. This number up here is what's called Euler's constant. And Euler is a scientist way more smarter than me. He came up with a way of mathematically describing something that is happening at a constant rate, okay? So what you need to know is that lambda represents 0.693 divided by half-life. You're gonna have to memorize that, 0.693. Put it in your head, okay? Because that's gonna be what you use to solve this equation. Lambda equals 0.693 over T1 half. Now you'll notice here that our lambda is negative. The reason it's negative is because, again, we're working with radioactive decay. So things are getting constantly smaller. I put that note right here. Negative lambda is because we're working with radioactive decay. So now that I've spoken a different language up here with all this other stuff, let's just break it down into what the equation is that you should use to solve these problems, okay? And that's the equation right here. This is the equation you need to memorize and stick in your head, okay? Memorize this thing. Just memorize it, memorize it. You're gonna go through a lot of these on your homework. It's tedious, but this will get it in your head, and I promise you these are on your boards. So here's our equation. Activity equals original activity times the log of negative 0.693 over half-life times time. Okay, that's the one you want to memorize. Now, on the boards, they may give you some of the things you need. or they also may say, they may solve this part of the equation for you and say, your decay constant is such and such a number. And in that case, you wouldn't need to put this in. I didn't do that with any of the homework because I want you to understand how to solve this using all the factors, which is likely what you'll get. So we can use this equation to solve for, again, activity, for original activity, for time, and for half-life. If we're solving for activity or original activity, we're going to use this little e to the x on your calculator. So if you get on a scientific calculator, it's going to have this little e symbol. A lot of times it's e to the x. I've seen some that are just the e. This is our logarithm function, okay? So when we get to that part of the equation, we're going to be using that function on the calculator. If you're solving for time or for half-life, you're going to be using this natural log or this ln function, which is the opposite of logarithm. It's the natural log, okay? So we're using these two functions. So you need to find these on your whatever calculator you're using. Find those functions on it because we'll be using them. I know when you go to sit for your boards, they allow you to use the Windows calculator. So you may want to search and find those on the Windows calculator and become familiar with that. I've just been using my iPhone, which has a scientific calculator on it, and those functions are on there. So let's work through a few of these so you can know what to expect. Now, again, things to remember, I've listed over here on the left-hand side. We want to get this right the first time, so don't try to cruise through these too fast. If you notice number 3, always write down that formula. Like I said earlier, when I went to take my boards, as soon as I got in there, I took a piece of their scratch piece of paper and I wrote down this formula so that I had it and my memorization days of it were over. You're going to always want to write down the quantities of the factors that you have. And then what we're going to do is we're going to fill in the equation with what we know, and then we're going to calculate and solve for what we don't know. At the end, when you get your answer, you need to ask yourself, is this reasonable? Does it make sense? Is it logical? That's going to help you, okay? So let's work through one of these. And when you look at these on your homework, it's written out as kind of a word problem. So with this one, for example, it might say something like, you have a 10 millicurie source of technetium-99. What was, or excuse me, let's back it up. Yeah, you have a tech source that was measured 2 hours ago to be 10 millicuries. What is the activity now, right? So in this case, we're looking for the present activity. 10 millicuries was the original activity. 2 hours have passed by, and our half-life is 6 hours because we're working with technetium-99, okay? So now let's come down and plug these in. Activity equals the 10 millicuries, and always write out your millicuries so you know what you're calculating, times by the log of negative 0.6993 times 2 hours. And I got that from my time, it's been 2 hours, over 6 hours, which is our half-life for technetium-99. You'll notice that I crossed out the hours because they're like terms. I don't need them anymore. So now I've got an equation. So now if you do the math here, we can start to solve this portion of the equation. So what I do is I take my calculator, I put negative 0.6993 times 2 hours divided by 6 hours, and I got this, negative 0.231. Okay, so there's what I got. Now, what you're going to do at this point is you're going to find that little e symbol on your calculator, that log symbol, and you're going to put negative 0.293, and then you're going to push this e button. When I did that on my calculator, I got 0.794. So my equation now reads, what that does when you do that, it takes it out of this logarithmic form into a normal number. So now I've got activity equals 10 millicuries times 0.794. When I do the math, I get activity equals 7.9 millicuries. Now I need to stop and ask myself, is this reasonable and is it logical, right? So my original activity was 10. 2 hours have passed by with a 6 hour half-life. I'm getting 7.9. That seems logical to me. That makes sense, okay? Let's do another one. So for this one, we were given our current activity and we're going to solve for original activity. We've been given a time of 30 minutes and we've been given a half-life. Again, it's technetium, so 6-hour half-life. Now, one thing to notice right away with this one is that we don't have like terms with our time and our half-life, and they need to be in like terms. So in this case, our time is 30 minutes, but our half-life is given in 6 hours. So you need to convert one of those. You can convert the 6 hours into minutes, you can convert the 30 minutes into hours, okay? I chose to convert my minutes into hours. In this case, 30 minutes is a half hour, which would be 0.05. So when I plugged in my equation, put 10 millicuries as my activity, equals the original activity, which I don't know, times the log of negative 0.693 times a half hour or 0.5 hours all over 6 hours. Then I canceled out my hours because they're like terms. So when I do the math and I take 0.693 times 0.5 divided by 6, I get this number here, 0.05775, negative 0.05775. So then I'm going to find my E on the calculator, my log function, and I'm going to take this number, plug it in, and hit that button. When I do, it gets rid of the logarithm, and it gives me 0.9439. So now my equation reads 10 millicuries is equal to the original activity times 0.9439. So I do the math on that. I want to get my original activity by itself. In this case, this number is being multiplied, so I'm going to go ahead and divide by that number. So if I divide by 0.9439 on the right side of the equation, I have to do it on the left side of the equation. On the right side, it cancels out, and I'm left with original activity by itself. On the left side, I divide by 0.943, and I get 10.6 millicuries. So the original activity was 10.6 millicuries. Now I need to ask myself, does it make sense? Is it logical? Okay, I have something with an activity of 10. So 30 minutes ago, with a 6-hour half-life, we probably should expect to be a little more than 10. And is that what we have? Yep, we have 10.6 millicuries. So it makes sense. All right. On this next example, we're given activity, original activity. We're not given the time, but we're still given the half-life. So now, remember, when we're solving for time or half-life, we don't use the logarithm function on the calculator anymore. We're going to use this natural log function. It's going to be a little different. So that's the first thing to pay attention to, is knowing that you're not going to use that function. Okay, so now we come down to our equation, we plug everything in. 9 millicuries is our activity equals 100 millicuries, which is the original activity, times by the log of negative 0.693 times time. We don't know what time is, all over half-life, which we know because it's tech. So a 6-hour half-life. Okay, now we can't go immediately into trying to solve and get rid of this logarithm. Why? Because there's a factor in here. There's an unknown factor that we don't know. So right now we can't do anything with this part of the equation. So we have to look over here to see what we can do. Well, we want to start getting this factor by itself. So what we can get rid of on this side is the 100 millicuries. What do? Well, it's being multiplied by 100 millicuries. So in this case, we're going to divide both sides of the equation by 100. Okay. If we divide the right side by 100, it cancels out the 100 millicuries. If we divide the left side by 100, we get this equation here. So we have now 9 millicuries divided by 100 millicuries equals natural log of negative 693 times time over 6 hours, which is our half-life. Okay. Now, at this point, we can cross out our millicuries because we have like terms. And so now we got to look at this. Now, here's the interesting thing. With the ln function on the calculator, you cannot use the ln function with a negative. If you have a negative in your equation, the ln function will not work, okay? So what we have to do is we have to find a way to get rid of this negative in the equation. If we look back to algebra, we have fractions. We can flip one side of the fraction. If we flip one side of the fraction, it gets rid of the negative on the opposite side of the fraction. okay? I'm sure when I was in your position, I had to review that. I probably didn't remember that from my algebra days, but that's what works. You can flip one side of the equation and it gets rid of the negative on the other side. So in this case, we take our 9/100 millicuries and we flip it. Now it's going to read 100 divided by 9 millicuries equals the logarithm of now positive 0.693 times time over 6 hours, okay? Now, at this point, what we can do is we can solve the left side of this equation, or at least make it a real number, right? So 100 divided by 9 is 11.11. So now our equation reads 11.11 equals the log of positive 0.693 times time over 6 hours, which is our half-life. Okay, now at this point, because we have a positive, we can use this natural log function to get rid of our logarithm. When you're using the natural log function, you're actually going to do the natural log to the number that's on the opposite side of this e. Okay, so in this case, what we're going to do is we're going to take 11.11 and we're going to put that in our calculator and then hit the ln button. That's going to give us, in this case, 2.408. Okay, so we're going to take that 2.408 and replace that over here. So now we have 2.408 is equal to, and now what that does is it allows us to take out that logarithmic function in here. So 2.408 is equal to 0.693 times time over 6 hours. Now you can solve this in a normal algebra equation that you're familiar with, right? So you can solve this fairly easily. So in this case, you could put a 1 under here and cross multiply. There's a bunch of different ways you can do this. I'm out of space on here, so I'm not going to solve this for you. If you don't know how to solve this, we can talk about this either at class, if you'll bring it to my attention, or you can contact me, but this is just normal algebra at this time. But when you run through and do this equation, you're going to get t equals 20.8 hours. So now I have to ask myself, is this logical? I started out with 100 millicuries, and it's all the way down to 9. So you can see just by that, if we went one half-life, which is 6 hours, it'd be 50 millicuries, right? If we went another half-life, it would be 25 millicuries, and so on and so forth. So is it logical that it's been 20 hours? Yeah, it's logical. Okay, so again, that one was solving for time. Our last one that I'm going to show you, we're going to solve for half-life. Okay, and this is very similar to the equation we just did. In this case, we're given an activity of 640 microcuries, 20 millicuries. Our time is 40 days, and we don't know our half-life. Now, earlier I had mentioned that you want to pay attention to what your factors are, right? The names, millicurie, micro, days, hours. We need to pay attention because we need those things in like terms to make the math work. So you'll notice on this one, this is in microcuries and millicuries, which means we need to convert again. We need to make them both in millicuries or both in microcuries. To go from millicuries to microcuries, we're going to move our decimal place to the left 3. I'm going to take this so that they're both in millicuries. Okay, so I'm going to take this 640 and my decimal place is here. I'm going to go 1, 2, 3, micro to milli. So when I inputted that down here in my equation, originally I put what the factor was up here, 640 mics is equal to 20 millicuries times the log of negative 693 times 40 days over half-life. I've changed it now to 0.64 millicuries is equal to 20 millicuries, and now I have like terms which I can get rid of, times the log of negative 0.693 times 40 days over half-life. Okay. Now, what are we going to do? We can't do anything to this part of the equation yet because it's a logarithm and it has an unknown factor, half-life. But we can do something over here. So we're going to do what we did before. We're going to divide both sides of the equation by 20 to get rid of this 20 over here. So when we divide by 20 over here, it cancels this 20 out. When we divide by 20 over here, we get this equation down here. Okay, so 0.64 divided by 20 is equal to the log of negative 693 times 40 days over half-life. See, how many times have I said that already? You're going to get it in your head. All right, now, remember what we did last time. We cannot work with a natural log function on our calculator when we have a negative. So what do? We use the algebraic principle that we can flip one side of the equation and it cancels out the negative on the other, okay? So we're gonna take and we're gonna flip the equation, and I've written it down here. We now have 20 divided by 0.64 times the natural log of a positive 0.693 times 40 days over half-life, okay? Now, when we do the math for this side of the equation, we get 31, so 20 divided by 0.64 is 31.25, equal to the positive logarithm 0.693 times 40 days over half-life. Now we're going to use our ln function on the computer, or excuse me, on the calculator. So we're going to find the ln of 31.25, and that equals 3.44. So now over here, we have an equation that's a normal algebraic equation. That's a simple one that you're used to seeing, which is 3.44 is equal to 0.693 times 40 days over half-life. And so now from this point, you're going to solve from half-life. Again, I didn't do it here because we ran out of space, but this should be a normal equation that you can solve from algebra, right? First thing we would do, and maybe I'll just walk you through it with words. I don't have it written down, but the first thing you do here is you obviously want to get half-life by itself, but you've got to get rid of half-life on one of these sides of the equation. So in this case, this number is being divided by half-life. So if we multiply both sides of the equation by t1 half, on this side of the equation, t1 half will cancel out. And over here, you'll have 3.44 times t1 half is equal to 0.693 times 40. And now you can solve it as a very easy equation. When we solve it all, we get t1 half equals 8.05 days, okay? Which consequently is I-131. So now by figuring out the half-life, we now know what isotope we're dealing with, which is a cool thing that you can do by knowing this equation, okay? Is it logical? Is it logical? It's been 40 days. And I went from 20 millicuries down to 0.64 millicuries. So there's not a lot left. It's been 40 days. If we were working with tech, there would be nothing, right? If we were working with rubidium, has a 75-second half-life, there would be nothing left, right? But because we're working with I-131, it makes sense that it has about an 8-day half-life. That makes these factors make sense. So again, I ask myself, does it make sense? And it does make sense.